Alrighty then, so what we have here in front of us is a number line, and a number line is helpful because it helps us actually organize numbers and just the way that they're related to one another. And so you've seen a number line before where we start with 0 in the middle, and as you move to the right, then we have our positive numbers, and then as you move to the left from 0, we have our negative numbers. Okay, and we know that 1, 2, 3, 4, 5, these are our natural numbers. Again, if it's 0, 1, 2, 3, 4, 5, those are our whole numbers. And then if we include now negative numbers, now these are our integers. So basically, what we see with our eye right now are the natural numbers. However, something very important to note is that there are numbers in between 0 and 1. For example, right here, I can put 0.1. Or maybe right here, I can write a half. And maybe right here I can put 0.6692, and I can keep going. And as a matter of fact, I can put infinite numbers in between 0 and 1. So, and I can put infinite numbers in between 1 and 2. And also, there are infinite numbers between 0 and infinity. So there are infinite numbers within infinite numbers. That sounds crazy. Yes, I know. For the Bible told me so. Well, okay, never mind. So basically, all the number line is just used to show us the relationship of how these numbers work with one another. Okay, so as you can see here, we can have fractions and decimals and so forth. All right, so how do we actually categorize numbers? We categorize numbers by grouping them. So I have two representations here. Let's just start over here. So the natural numbers 1, 2, 3, 4, 5 to infinity, those are called the natural numbers. Okay, so this is just kind of like a graphical way, or just kind of a visual way of representing this. And then I have the same thing over here. So this capital N, which means natural numbers, is the set of elements that start with 1, 2, 3, ... which means it goes on forever. So this guy right here, this is the same as that. Those are equivalent. So basically, I'm showing you the same thing twice here using our set notation, and here I'm just writing this in this diagram here. Okay. And then the whole numbers include 0, and so that's where this comes in. And then the integers is the natural numbers, the whole numbers, and the integers. So this guy is going to be the same as this, and as you can see here, that's why it's 0. That's the whole number, 1, 2, 3, 4, 5, and that's where we get the natural numbers, and you put the negative numbers in there, and that's where you get the integer. So these two are equivalent right there. Let me get a different color here, maybe. Oops. And then the rational numbers, which rationals Q, integers are Z, which is the way that we did this in mathematics. Now, a rational number is okay. So it's the set of all numbers P over Q, okay, where P and Q are within the integers. So P and Q have to be an integer, and actually a rational number is any number that can be written as a P over Q, or in other words, a fraction, a rational number. So if you can write a number as a fraction or as a decimal, then that means we call it a rational number. Now let me just make a quick note here, and that is your decimal or your fraction. Actually, let's talk about the decimal. The decimal, in order for it to be a rational number, has to either repeat or it has to terminate in order to be a rational number. So for example, the number 0.6 with a line over it is 0.66666666666 and forever, so that means it repeats, so that's fine. 1.75, see how that decimal terminates? I mean, like, it stops, so that constitutes a rational number. If I have the number 1.2345, okay, well, it doesn't repeat, but it does terminate. Okay, so but decimals like the square root of 2. Square root of 2, 1.141 59, and then it keeps going. See, that decimal, if you put square root of 2 in a calculator, and if you calculate to 10, 20, 30, 100 decimal places, it neither repeats or terminates. If it doesn't do either one of these, then it's not a rational number. Okay, and then lastly, we have the irrational numbers. Okay, so these are the irrational numbers, and the irrational numbers are numbers that cannot, basically, check this out, it's all x values such that x is not within the rational. So if it's not rational, then it's called irrational, meaning if you can't write it as a repeating decimal or a terminating decimal, then it's going to get kicked over here. So like square root of 8, negative square root of 8, square root of 15, pi over 4, square root of 3, square root of 7, square root of 9. Is that an irrational number? No, right? Because square root of 9 is 3. So actually that would actually get plopped over here. Square root of 10, square root of 21, square root of 51. So all these would be irrational numbers because their decimals don't terminate, neither do they repeat. Alright, so let's do some examples now. So I have these set of numbers, and I have my little diagram right here to help us out. Let's categorize all of these that are whole numbers, which ones are integers, which ones are rational numbers, irrational numbers, and real numbers. Okay? Let's start with the whole numbers. So which of these are going to be whole numbers? Again, whole numbers are 0 and the positive natural numbers. So right here, square root of 4, right? Square root of 4 would be a whole number. Pi, no, and 1.12, no. So those are the only whole numbers. How about integers? Again, integers are all the natural numbers, whole numbers, and the negative integers. So that would be negative 7, square root of 4, and that's about it. Rational numbers. Numbers that can be written as a fraction. Okay, so can I write negative 7 as a fraction? Heck yeah. So good. How about 3.14? Can you write that as a fraction? Or does it have a decimal that terminates? Ha ha, it sure does. How about the square root of 4? Well, of course, right? Because square root of 4 is 2. So square root of 4. How about pi? Remember, pi is a decimal, but it neither repeats nor it terminates. And then 1.12, it is a repeating decimal of 1.12. Irrational is the only one going to be pi. And all of these numbers are real. Okay, for this class, we're going to be talking about just real numbers. We'll get into complex numbers in later on. Okay, so let's go into example number 2. Example number 2, or example 4 actually. We're going to decide whether the statement is true or false. And if it's false, let's explain why. So all integers are irrational numbers. Are all integers irrational numbers? Well, if we go back over here, are all integers irrational numbers? Okay, so let's think about this here. Well, isn't it true that all integers are rational numbers? Right? I mean, integers fall in the rational category, not irrational. And so we're just going to say that that's going to be false. And actually, let me just take this diagram. I'll just copy this over. And we'll just use this as a little sheet right here. Cool. So this answer is going to be false. It's going to be false. And our reason is going to be this, is that all integers are rational, not irrational. Okay? Every whole number is an integer. Every whole number is an integer. Well, of course, right? Because the whole number is encompassed within the integer. So, true. Bing! Some integers are whole numbers. So, some integers are whole numbers. Well, yeah, right? Because the integers are -1, -2, -3, 0, and 1, 2, 3, 4, 5. So, some of the integers, which happens to be 0, 1, 2, 3, 4, 5, are part of the whole number. So, true. Okay, but not all of them. If this said all, then it would be false. Every real number is irrational. Every real number is irrational. Well, wait a minute. Didn't we say that real numbers are irrational and rational? So this would be false. So we would say real numbers are rational, Q, and irrational I. I'm just going to use the mathematical notation there. So all numbers or real numbers are rational, or I'm sorry, not and, but they're or. So they're going to be either one of these two categories right there. So we'll say or. And there's example 3 and 4.